So welcome everyone. We're very happy to have Pim van der Hoorn here today from the TU in Eindhoven, speaking about geometry and complex networks, a powerful partnership.
Yes, so thank you very much, Anders, for the invitation. It's very nice to be here. It's actually a very nice location. I mean, I often travel to different universities, and every now and then I'm very sort of envious about what locations universities have to give these seminars. So the talk today, I'm a mathematician, and mathematicians are terrible at coming up with titles. Luckily, I work with physicists. Physicists are way better in coming up with titles for papers and all sorts of things. So I try to learn a bit from them, and this is why I sort of try to pick a bit more sort of engaging title. So I have a plan today to talk about sort of two aspects where I'm trying to show you sort of the interesting relationship between analyzing networks and using geometry. But I just wanted to start by saying, so I have a plan for today, but please feel free to interrupt me and start a discussion. I would much rather talk about questions that you have and make sure things are clear than going through the entire plan I have. I mean, this is all optional. So having said that, let's start. So I work on research where we are trying to study complex systems, or in general complex networks. And I guess for this audience, right, you understand that there are lots of different types of networks: social networks, technological networks, biological networks, and way more. And these are often, these represent often complex systems that we're trying to understand. We're trying to understand certain emergent behavior that comes up from these systems. We're trying to understand how these systems evolve over time. I don't need to unmute myself because you can hear me, right? Okay, great. So, and we're also trying to sometimes understand how processes develop on these systems and make predictions on these processes. And so in general, there we go. In general, so the goal is to understand, predict, control these complex systems. And I'm trying to contribute to this general goal. And basically my research is about developing models for these complex networks. And this is, for this, and I'm using probability theory. And that means that the models I'm considering are what are called random graph models. So the general goal that I'm trying to accomplish is to design certain random graph models that can be used to model specific types of complex systems. So complex systems with specific structure, specific behavior. And to do this, I use geometry. And as the title also shows, geometry is sort of the star of the talk today. Okay, good. Okay, I heard some some echo. And now, if I'm talking to physicists, I mean, I don't have to explain to you that geometry is a powerful thing.
You might unmute yourself on your laptop, so maybe you mute yourself.
I'm very sorry for that. Okay, great. So physicists know that geometry is a powerful thing. I mean, this is used in lots of developing lots of theories in physics. And in particular, and this is how I got involved with a group of theoretical physicists, it turns out that they're also using this to study and better understand gravity, and in particular quantizations of gravity. And I have to sort of make a caveat here, right? I'm a mathematician, and I find these things very fascinating, but it's really difficult for me to understand all of the intricate details there, even after many long talks and discussions with experts in these fields. So you can ask me questions about how this relates to quantum gravity. In general, my answer will be, well, I can point you to the people that will give you the answer that you seek. So, what they're using different types of approaches. There are causal set approaches where geometry is an important part, and starting with the discrete geometry, going to continuous geometry. This is what they're trying to do there. And in particular, recently, people have been trying to use some sort of very rudimentary forms of random graphs to sort of model this sort of continuous geometry emerging from discrete structures. Now, outside of physics and mathematics, I mean, latent space models, so models where there's some sort of latent space present, that have actually been used for a very long time already in other fields such as sociology and psychology. And so here the idea is really that when people try to study sort of how people or humans behave, they see humans as being part of some sort of latent space that encodes similarities or dissimilarities. And then by understanding where people are in this space with respect to each other, they can make predictions about how you will react or with people you will interact. And so in general, from this perspective, usually what we understand is we are studying some system, and the system has entities, and these entities are somehow present on some space, some latent space, usually a space that has a geometry that makes it much nicer. And then we can use this space to build models and also use the space to make predictions about the models. And this is what I'm going to do in the first part of the talk. So I'm going to try to explain how we can utilize geometry to build better models to study complex networks. Now that is of course one way, but actually there's another. You can also look at the arrow in the other direction, and that is actually a bit both more challenging but also more interesting. And that is, well, suppose that somebody gave you some sort of network that was created using a latent space. Can you then extract information about the geometry of the latent space by just looking at the network itself? So you're really asking sort of a question about, I have a discrete structure, and does this discrete structure somehow encode information about the geometry that was used to build it? And this is what I'm going to sort of touch upon in the second part. And combining these both parts, I somehow hope to sort of make good on my title and show you that there's indeed sort of a powerful relationship here between networks and geometry. So having said that,
sorry, can I ask a question?
Yeah, sure. Yeah, please.
So you're saying, yeah, you reconstruct the geometry, but you're going to apply this to spatial geometries or space-time, because the quantum gravity business does more like, yeah, right. So is it spatial geometries or?
Yeah, so for this talk, I'm going to consider just some vanilla sort of Riemannian geometry. So there's no Lorentzian geometry here. This is what my collaborators really like to move towards. But the challenge, I mean, Riemannian geometry was already quite challenging. So it will be even more challenging to extend this to Lorentzian geometry or other types of geometry that are more related to space-time.
Okay, so it has nothing to do with causal sets then?
The research here has nothing directly related to causal sets, but
okay.
It is inspired by questions from causal sets, because this backwards arrow, right, from the networks to the geometry, that is something that they would really like to do in these causal sets using the Lorentzian geometry features.
Right.
And so, to give you a bit of a backstory, basically they asked this question. They say, oh, we have this network, can we somehow reconstruct properties of our underlying geometry? And then we said, oh, that's an interesting question. Well, I mean, we always go as mathematicians to the simplest case. So we said, you know what, let's first look at Riemannian geometry, see if we can do something there. And so the hope is that, of course, these things can be extended.
Okay, thanks.
Okay, so the first part is on using geometry to model complex networks. So, and here I just have to give you a bit of a flavor of the type of approach that we use in this modeling. So the idea is that you're given some complex system, and this system has certain properties. And these properties are deemed to be important from a domain specialist point of view, right? So there are domain specialists that come with this complex system, they study this and they say, well, this network has certain properties that we know or we really think that are sort of defining the system. And so then if you want to build models for this system, what you really want in this case is you want to build, from my perspective, a random graph model that mimics these properties, but not, of course, not exactly. That is always quite difficult. We want to mimic these properties sort of in some sort of asymptotic way. So what we're saying is, right, as the system size grows, the properties should converge to the values that we have on the system that is given. And there are several reasons why we're doing these asymptotics. First of all, usually the systems that we're trying to analyze are already quite large, meaning that sort of these asymptotics should be sort of this asymptotic state of the model should be a very good representation of this very large system. Another thing is, of course, that limits are slightly easy to study. And I also noticed from my physics training that there are two things that are easy: very small systems or infinitely large systems. And usually everything in between is very difficult. So here we're sort of taking the easy road. We're saying, okay, look, we're just going to study the limits. That's at least easier from a theoretical point of view, but also as long as my complex system is large enough, it will be a good approximation. And finally, of course, studying limits also makes the results a bit more robust to fluctuations, and we can also, in some cases, even quantify the variance sort of fluctuations that we get. So that brings us to, so this is the approach. So that brings us to the next question. Well, okay, you want to model certain properties. So which properties do you want? And now, of course, in general, that depends really on the specific system we're analyzing. But there are a class of properties that we often see in networks. And I want to sort of touch upon 3 of them here, because they will be sort of the motivation for the model. And the first has to do with the degrees in networks. So often what we observe in many complex systems, complex networks, is that the degree that they are sparse, meaning that the sum of the degrees scales linear with the size of the graph, which I denote here by n. And so another way to formulate this is that if you look at the average degree of your system, the idea is that as n grows, that should converge to some constant. So it should have finite average degree in the limit. Now, in addition to being sparse, we often also see some specific form of the distribution of the degrees. And this is sometimes called, this is sometimes referred to as power law degrees, or other people use the term skill-free degrees. I mean, there are lots of nomenclature there. But what it is about is that we are looking at the empirical distribution of the degrees, so just a fraction of nodes with a given degree. And then if we plot this on a log-log scale, and here this is done for the internet, you see a certain type sort of behavior. Something like a straight line, almost, not exactly. And you sort of see this at a very rough scale, you see this type of behavior for degree distributions also in lots of other networks. And the idea is, of course, here the intuition is, if you look at these plots, you sort of squint your eyes, right? You can sort of start seeing these linear decays happening. Now, if you have a linear decay, on the log-log scale, right? You have that formula here. You have this formula here. Now you take exponents on both sides, and then you somehow see that what this means is that your degree distribution falls off as some sort of inverse power of k. And in order to make all these things nice, this power has to be at least bigger than 2, because else it's not. They won't have finite average degree. Yes.
I don't know if it's the right time to interrupt. But
no, it's always the right time to interrupt. Please.
So one of the controversies here, right, is this. So you know the work by Aaron Corset, right? It's,
yes. Yeah. I'm very much part of this controversy, I'm afraid.
Okay. So, but then this assumption that you make about the small or the large systems, actually the details matter.
Yes, exactly.
The scales matter, the size matters. And I wondered, there's also some work, the fact that we see these power laws everywhere. There's some work by Stephen Turner that shows that these can be actually quite trivial. It's almost like seeing a Gaussian distribution. There's so many ways that you can generate these power laws.
Yes.
And I wondered whether this geometry that you find can actually tell you something about how surprising, or rather, trying to fit properties, but would you expect that property? Is it easily explained when you see the geometries all look kind of similar with certain properties, then this is just a natural outcome? Yes.
So that's actually a very interesting question. So what often happens is, and yeah, I can touch upon this later, but I will describe a model that uses geometry to build these networks, and this model there's physics intuition why we're using this specific model, but there are also different variances of this model that somehow decouple, in some sense, the contribution. Basically, they decouple the geometry versus some sort of hidden variables on the nodes. And it turns out that these hidden variables are the main culprit for the degree distributions. So in that sense, coming back to your question, for those models, the geometry doesn't really do anything for your degrees. That doesn't mean that for other types of models, geometry might be a culprit. But usually, and this is also what we see later on, geometry is often there as to make sure that the networks are more clustered than you would expect for most graph models. But actually, so coming back to this question, so indeed, so what happens in the early days of network science, people studied saw these power laws already very early in citation networks, and then at some point it took off, and then people claimed, oh, power laws are everywhere. Now you can talk to me after this presentation whether or not that is true. Of course, it's not true that power laws are everywhere or they're nowhere, right? The truth is always in the middle, but you really have to indeed. First of all, you have to come up with the right definition of what you mean. I mean, the one here is very strict, and there's a twiggle sign, right? And actually, this twiggle sign is sort of a problem. So there are lots of things you can do there, and I have some papers on this. So if you're interested, please ask me later. So one of the things that is here, what we want to do, if you want to do it more mathematically, the problem is that this is basically the probability mass function, right? It's the fraction of nodes with a fixed degree. That's often not sort of the most stable thing to look at. So often in mathematics, we often like to look at cumulative distributions. And when we are interested in power laws, we look at the tail. So the tail cumulative distribution. So that's just a fraction of nodes whose degree is strictly bigger than k. And you can show that if your degree probability mass function has a power law, this also has a power law. The converse is not true. So this is more general. So in general, what we ask here is we ask, well, this empirical tail distribution should converge to something that looks like a power law. And what we mean here is it should converge to a regularly varying function, which is some power law term together with this L of k, and this L of k is a slowly varying function. These can be constants, things that converge to constants, logs, powers of logs. But the nice thing is all of these functions, when you plot them on these log-log scales, you will see these straight lines, even though they're not exact, right? There are some slowly varying corrections, but it's sort of a more broader model in that sense, right? Like you said, it's basically an infinite, uncountable family of models that give you power laws. Yes.
Can we come back to the business about why the exponent has to be bigger than a certain value?
Between 2 and 3.
Yeah.
Oh no, between 2 and 3. That I mean that is only true in a certain case of models. Bigger than 2 is there to make sure that the limiting distribution has finite mean.
Yeah. But why?
Yeah, between 2 and 3, that is often.
No. I'm saying you do the finite mean. Why do I care about the finite mean?
Yes, well, that is because I mean we make sort of we make this empirical assumption that sort of the degrees are linear in the size of the network. So if I'm assuming that the average degree converges to a constant, then my degree distribution has to converge to something that has finite mean. I mean, else these things are not. And there are definitely instances of specific systems where this assumption of finite mean is not needed. And then you can change this. Then this exponent just has to be bigger than 1 to make it normalized.
Because we can always make this in the case of statistics, we can always take the so-called moment distribution. So basically just renormalize the thing by its moment. And you can increase the exponent. The concrete example would be that take a distribution with power law with the exponent say 1.5.
Yes.
Okay, and then say I'm going to weight it when I form a new distribution s times f of s. And that thing's going to be heavier tailed by one increment, but it's still a meaningful distribution. Yes,
exactly. Yeah. No, and for instance, it is a meaningful distribution. For example, if you have a distribution and you look indeed at s times that distribution, you normalize it by something. That's what's called the size bias distribution. Exactly. That's basically the distribution you get when you ask, well, what's the degree of a node that has at least 1 degree, right? So it's a degree of my neighbors. And that can have infinite mean, and that is actually, for instance, very relevant for getting short path lengths, for example. So distributions with infinite mean are definitely interesting, and they also come up in this work, but the degree distributions, in order to make them sparse, we often...
So it's basically an empirically driven argument. Most of the real numbers are sparse, therefore... Yeah,
therefore we make this model assumption, and that is...
But okay, now that's a different point, because I can say that, you know, there is this old method, without going too far in detail for it, in 55, when Simon paper in biometric about the Ewell-Simon process, right? And then Mandelbrot attacks it, right? And Mandelbrot's basis for attack is to say that Simon's model permits exponents to be less than 1. Mandelbrot says there can be no real empirical data for which exponent can be less than 1. He says that, right? And then there's this back and forth for 5 years where they're fighting each other, right? So I just think that I mean, there are many examples I think today where you just construct examples where the exponent's less than 1, less than unity, right?
Yeah. Exactly. No. So I would not claim that it doesn't make sense to look at those. But in order to make sure that everything's sparse in the end, I mean.
Right.
But if the exponent is less than 1, you cannot normalize distribution, right? Like you're saying, you can reweight it so that you can normalize it.
Well, it's still a valid distribution. So what do you mean by renormalize?
Because your integral from 0 to infinity is diverging, right?
It depends on which exponent you mean, right? So if you talk about this beta exponent, right?
If beta is less than 1, then there is a problem.
Yeah, but the exponent of this can be less than 1 of the tail.
Oh,
It can
yeah,
be
yeah.
less than 1.
Yeah, I see.
And you can actually push it arbitrarily close to 0, of course. It just means that the average degrees are not going to explode. And that does make sense in certain systems, right? So there are ways.
Yeah, right. So which is what I work on, it makes eminent sense.
Okay, so those are degrees, right? And then, so those are basically the 2 properties with respect to degrees, so sparsity and these regular varying tails. And then the second property that we often see is that networks are often, they are clustered, meaning that there are some sort of notion of communities or nodes are more, you can sort of see nodes that are more sort of clustered together than to the outside. And in particular, one driving thing of this clustering is sort of triangles. So we often see many triangles in these networks. And so there are different ways of quantifying that. So one way is what is known as the global clustering coefficient. And that just basically counts the total number of triangles in the system, which is given by this delta G, divided by the number of wedges, which are just paths of length 2. So those are things that could be triangles. Another way to do it, so this is at a very global level, right? So you just look at the entire network, all triangles and all things that could be triangles. But there's a different way to look at it, and these things are not equivalent. So there's what you can also ask is, well, I look at every node. A node has a certain degree. That means that the total number of triangles it can form are the degree choose 2. So then what I'm doing is I'm counting the number of triangles in this node, normalizing it by the maximal number, which is the degree choose 2. And I'm just going to take the average of that number over all nodes. That's what's called the local clustering coefficient. So that's clustering more at the local level. And in particular, for our models, we are going to assume that this local clustering coefficient converges to a non-zero number. So there is clustering. And finally, you can make this local clustering function a bit more specific by saying, well, instead of looking at all nodes, I'm only going to look at nodes with degree k. So for every k, I can do the same thing. I just look at all nodes of degree k and compute this local clustering coefficient. Then I sum it, but then of course I need to normalize by the total number of nodes of degree k instead of the total number of nodes. So this is a function of k. And what we're going to assume is that this converges. So this empirical function converges to some limit function as n goes to infinity. You can ask, well, what limit function? Well, there's evidence for many networks that this here you see this function plotted for real world networks. There's again this evidence that this function is regularly varying. But here actually you get exponents that are very close to 0. So this is in general an assumption we're making that this function should converge to some regular varying function. Okay, so just very quickly, right? These are the structural properties for now that we see in many networks. So this is the question. This is the challenge, right? Can we already build a model for these properties? And that is sort of a baseline. I mean, this is something we see in many networks. So if you want to build models that are relevant for specific given systems, we should at least be able to somehow model these properties together. And that already turns out. So this gives us this question, right? How can we construct this model? And it turns out to be already sort of challenging. So let me just quickly sort of tell you what the most known models, standard models can do. So here are the 3 properties. And there are lots of classical models for networks. So the most classical, of course, is Erdős-Renyi or the sparse version of Erdős-Renyi, right? Where you just drop edges independently with the probability that you now divide by n. Then you get a sparse network. But the degrees are not power law, they're Poisson if you not do anything. And there's no clustering. Now, you can, in order to sort of go to more general degree distributions, you can use other models such as the configuration model, where you start with either a given degree sequence or sequence sampled from a distribution. And it's also sparse, but again, no triangles there. And same holds for other more nicer models. So things like the preferential attachment model, where nodes come in and attach preferentially to the nodes with the largest degree, or generalized random graphs, which are basically generalization of Erdős-Renyi model, where you now allow the probability of edge connections to depend on some hidden parameters that are node-based. So all of these models are sparse and can generate power law degrees, but they don't have triangles. So that turns out to be difficult. So how to get the triangles there? Well, but if you think about, well, of course, given the talk, I mean, you have to use geometry, but it also makes sense because if you somehow build a model where nodes are connected based on their proximity, then because of the triangle inequality, if 2 neighbors of a given node are by the triangle inequality more likely to be close and hence more likely to be connected. So the triangle inequality from geometry sort of gives you a more likely opportunity to see triangles. And so this is the idea. You have some geometric space, you drop some points in there, and then you connect points with a probability that is proportional or inversely proportional to their distance. And then you generate a network, and this network will have geometry because of the triangle inequality. And then the question is, well, which geometries can you use? There are lots of options, there are lots of ways for this models. But the first model that was able to combine these three was a model which is sometimes referred to as the the KPKVB model, which are just the letters of the authors of the thing. And that model uses hyperbolic geometry. So there the idea is the underlying space is a hyperbolic geometry, and then we just throw points there, we connect them based on their distance in the space, and then surprisingly, we get all of these three features out. So usually when I give this talk, I always present some sort of background on hyperbolic geometry, hyperbolic plane at a very high level. So let me just quickly go through this if you haven't heard this. So the hyperbolic plane is the idea, it's a surface of constant negative curvature, and here we're going to take this curvature -1 in order to renormalize it if it's something else. Now you can ask, well, what does this look like? I mean, we can imagine what Euclidean space looks like. You can sort of imagine what spherical space looks like. Well, hyperbolic geometry is a space where every point locally, every local neighborhood looks like a saddle point. Well, that's a local description, but that's not a global description. Actually, it turns out it's very difficult to give you a very global description. It's even it's impossible to embed a hyperbolic plane in three-dimensional space in an isometric manner. So that's a mathematical result. And actually, and this is all if we require the embedding to be sort of 4 times continuously differentiable. So that's already, I mean, that's sort of a very sort of slack requirement. But even then, we are not able to do it. And so actually, a co-author of mine, right, found this very nice picture in some book, which considered sort of a C1 isometric embedding. He showed that one exists, it's not constructive, and then there was an artist's impression of what it would look like. So this is what it looks like. This is just to show you that it's very difficult to imagine this plane of constant negative curvature, right? So we're not going to do that. We're not going to imagine this. I'm not going to give you any embedding. I'm going to give you a representation of this space, and the representation I'm going to use is the Poincaré representation. So the idea is that you just have a disk in 2-dimensional Euclidean space, and now you put a metric on this, and the metric is this. And this is a model for hyperbolic geometry. Now, and you might have seen this. So this comes up in pictures by Escher, and this is one. It's called the circle limit 3, I think even. So this is basically the tiles that you see here are actually in the hyperbolic space, and this is the Poincaré representation of that hyperbolic tiling with these fishes. Now, often it's a bit more easier, and also for this model to use, instead of the Poincaré representation, to use what is called the native representation. And that's basically sort of expanding this to the Euclidean plane. So that's basically, we're doing this transformation at the bottom here. And if you do it, for instance, on this circle limit, this is a finite slice, of course, of what you got. I can't draw the entire Euclidean plane here, so this is a sort of finite slice. And this is the representation that we're going to use. So that means, from now on, right, when we talk about hyperbolic space, it will be, the points will be in the plane, and there is a metric defined by this transformation on the metric on top. You don't need to remember all of this, just you can think about the hyperbolic plane in this way. So with that, I can now describe to you the model. The model is quite simple. So it was introduced in 2010 by Kryukov and al. As a model to unify these 3 properties. It has several parameters. N is, of course, the number of nodes. There's an exponent alpha, which should always be bigger than 1/2 for the network to be sparse. You can think of this exponent as tuning the exponent of the degree distribution. There's an exponent nu, which controls the average degree. And then there is an exponent r that comes from these 3, and that controls the connection radius, basically the hyperbolic radius in which points connect to each other. Now, the model is very simple. You start by sampling endpoints uniformly at random on the hyperbolic disk with radius Rn, uniform with respect to the metric. And then what you do for any 2 points, you look at 2 points, and if they are within distance Rn, you connect them. It's a very simple model. Now, if we transform this to the native representation, it becomes as follows. So now we sample points on the Euclidean disk of this radius Rn, and we denote the points in polar coordinates, so radius and angle. And then the uniform distribution on the hyperbolic space then translates into this distribution in the native representation. Don't need to know what it is. It has some form. You can already see some cosine hyperbolic, sine hyperbolics, which are there because of the hyperbolic geometry. So you sprinkle points with this density, and then now you connect two points if they're close, if their hyperbolic distance is less than r, and you can sort of translate this into a nicer formula by using the hyperbolic cosine rule, and that basically gives you this. So what you do is you take 2 points, you look at their angular distance, which is this, it's the distance on the left here, and then if it's less than this expression on the right, which only depends on the radii of the radial coordinates of the points and the connection radius Rn, and if their angular distance is less than this number, you connect them. So this is the same model, but now in terms of this native representation.
So in the hyperbolic space, the distance increases if you go to the edge of the disk, right?
Yeah, in the Poincaré indeed, so the disk is basically infinity. The boundary of the disk is infinity, but now we map this to the Euclidean space, right? So infinity is really at infinity.
But so the radii, okay, so the radii, okay, no, okay. So I was thinking because if you were to only look at the angular distance, right, not the angular difference.
Yeah, no, it's the angular distance in the Euclid so it's the angular distance in Euclidean sense, right? So it's it's really this difference between the angles modulo 2 pi. So it's really just the angular distance in the Euclidean sense. It's not the angular distance in the hyperbolic sense.
Okay, yeah.
So just to give you sort of an example of what this looks like. So here's a realization of the points in the disk. And now we look at the point all the way at the boundary. And what I draw in the dark shaded area is sort of the hyperbolic disk of radius Rn. So these are all points that should be connected. And now the thing is that if you move closer and closer to the center, sort of you get these lollipops and they blow up in such a way, of course, that if you're close to the center, your connection radius becomes large, you connect to more points. And all the way, of course, and then in the end, you get something like this. And this is just so that you have sort of a flavor of what these graphs look like. So the idea is nodes with large degree are more towards the center, and nodes with low degree are more towards the boundary. And there are more nodes at the boundary than at the center. And this already sort of gives you an idea of why you might expect some sort of heavy tilt degree distributions, like less nodes with very large degrees. Now, and this is indeed what you can prove. So several of these properties were analyzed in the original paper by Kryakov and co-authors. This was, of course, a physics paper, so then at some point there were some little caveats. So at some point, mathematicians said, "Okay, we'll fix these last little main things." And in particular, Gugelman et al. Had a nice paper where they basically went through these computations and sort of filled in the little gaps. So they proved that the model gives sparse graphs where the average degree is basically given by this number there. So that's good. They also proved that they have power law degrees. So what they proved is that the empirical degree distribution converges to some function, and then they showed that this function is basically of this order of power law. They didn't. This is a very high level summary of their results. Their results are more specific, but this is basically the takeaway. So these degree distributions have power laws. And then clustering, they proved that the local clustering coefficient is bounded away from 0 and away from some constant with high probability for very large n. So that somehow tells you, yes, there is clustering, but it still leaves lots of room open, right? For example, I mean, this result doesn't tell you if the local clustering coefficient actually converges to something, right? It can just fluctuate between these numbers. And in particular, they had no results about the local clustering function itself. So this is what we set out to do in this work. So we're trying to basically prove that the local clustering coefficient converges and that the function converges as well, and also try to sort of pinpoint down these limits exactly, which was a terrible exercise, but in the end we managed to do this. So just to give you a short, just a recap, these are the 3 properties. So we have a global clustering coefficient, which we didn't consider. We looked at the local clustering coefficient and the local clustering function. So I will briefly tell you what was known before we started. So the global clustering coefficient was already investigated by one of the co-authors, Nicolaas von Tlaakits and his PhD student, and they proved that it converges to some constant for a specific range of alpha, and if alpha is bigger than 1, it converges to 0. So the global clustering coefficient converges to 0 for alpha bigger than 1. Now again, this is the result by Gugelman et al. So that was known. And for the local clustering coefficient, not much was known, except for some conjecture from the original paper, where Kryukov and co-authors basically they sort of computed it. They did some sort of bounding and some sort of changing intervals and limits. They made some sort of computations, and then they checked this with models, and then they conjectured that, well, this function should decay as 1 over k. Basically, this was their conjecture. All right. So we studied both the local clustering coefficient and the local clustering function. So what did we get? So here's a recap of the local clustering function. And what we got is indeed it converges to a constant. So as long as alpha is bigger than 1/2, which you need for sparse graphs, and your average degree is bigger than nu is bigger than 0, though that's what you need, then there is some constant that depends on alpha and nu, such that the local clustering coefficient converges to this constant. And we can even do better because we know what the constant is. I can't give it to you here because it's a terrible thing. It basically includes all the special functions that you can think of, including certain instances of the Meyer G functions that didn't have any other types of representation. So here is just sort of the first few lines of what this thing looks like. And there are other things down there, just sort of, but just to show you, we know what the constant is. We can compute it. If you give me alpha and nu, I can put them into my computer program that does numerical integration and use these special functions. It can compute it. Now, in general, what we got, this expression is only valid for alpha not equal to 1, and that is because, as I said, so you have beta functions, these types of things. But there are some exponents, there are some problems that alpha is 1. But we can show that these poles are basically vanishing. So we can show that the limit of alpha going to 1 of this expression exists, and that will actually be the corresponding constant when you pick alpha as 1 in this case. So that is the result for the local clustering coefficient. And then we went, of course, we thought, okay, let's go one step further to the local clustering function. This is the formula for it, and we were able to show that it converges to a given function, but we were able even to show more, because we were able to show that it converges in such a way that it actually has the same scaling as the limit function. So what this result tells you is that if you look at the local clustering function, for a graph of size n, for some sequence of integers that can also grow with n, then there is a limit function such that the fraction of these two things actually they are basically asymptotically equivalent in the probabilistic sense, meaning that if you take the fraction, you subtract 1 from it, that thing converges to 0. So that doesn't only mean that it converges pointwise, but it converges uniformly up to any sequence of k that grows slightly less than n to the 1 over 2 alpha plus 1. So that's actually quite nice, and we have we know exactly the limit function. In particular, it's some constant that we can again exactly compute. It has nicer forms than what I showed previous, but I mean it's still a bit long. But what is more interesting here is that the scaling behavior of this limit function, which is also again the scaling behavior of the local clustering function, it actually has different scalings, and there's a phase transition here. So in particular, the conjectured 1 over k scaling is true as long as you pick alpha bigger than 3 over 4. In terms of the degree distribution, that means that your degree distribution, if you look at the probability mass function, it needs to have an exponent at bigger than 2.5. However, if your alpha is between 0.5 and 3 over 4, then the function decays with an exponent that depends on alpha. And please note that if alpha is 1/2, then the exponent here is 0. So it can be the closer you pick alpha to a 1, the closer this exponent will go to 0. So it becomes more flatter and flatter. And then there's a phase transition. In the middle where there are some logarithmic corrections. But of course, in the end, right, this basically proves indeed that yes, this clustering function converges to a regularly varying function, which is what was observed for many networks and what we set out to do.
Why is there something special at 3/4?
That's a very good question. We looked at different literatures to see if we can get some physical meaning of this. There are some examples where people were modeling using complex networks to model, say, flocks of birds, sort of emerging behavior there. And there was also some very interesting phase transition happening exactly at the same thing. But I mean, this was just an example of another place where they found this, had this 3/4, 2/5 thing. Currently, with a student, we actually are doing this analysis on a more broader class of models, and he actually figured out that there's a specific type of stochastic variable that is basically the culprit of this entire thing. Basically, when this stochastic variable has finite mean, that is when you have the 1/k, and when it doesn't have finite mean, you're in the other regime, and that happens exactly at this transition point. So mathematically, I can tell you why there's a transition. I have no idea what it means in terms of maybe the geometry here. That is still some open question that it's very, very interesting but difficult to answer. Now, these are conversion results, right? But we also did some simulation, basically show that indeed the theory works well with, already works well on practice. These are results for graphs of size 10,000. That's not too big. The points are simulations over 100 graphs. This is the average, and the lines are the theoretical predictions. It's just to show that indeed already for very small sizes, these theoretical results are very good predictions of what is actually going on in the models. Both for the local clustering function, which is on top, for different values of alpha plotted on the x-axis and different values of nu for the colors, as well as for the local clustering function here. All right, so that was the first part. So that was the part where I'm saying, okay, I want to build a model and I'm going to use geometry, in particular hyperbolic geometry, to give me a model that's of the nice properties. Now the second part goes the other way around. So that's basically, okay, somebody generated a model based on geometry. They give me the network. And now the question is, can I somehow infer some sort of geometric properties from that network? So can I infer some sort of continuous scale properties based on discrete information? And of course, the most general property to look at is curvature. Curvature is sort of the intrinsic property in general of geometric spaces. And in general, the idea is, of course, curvature is somehow a measure of how much your space deviates from Euclidean space. So Euclidean space is the space with zero curvature. If we're asking for negative curvature, that was the hyperbolic space that I talked about before, and positive curvature is about spherical spaces. Now, there are different notions of curvature if we go to the general notion of Riemannian manifolds, which is something that I will be focusing on here. So when you want to study curvature of Riemannian manifolds, you can do it using sectional curvature, Ricci curvature, or scalar curvature. They are related, not always equivalent. It depends a bit. In this talk, I'm going to focus on Ricci curvature. So very specifically, the question is, if I take a Riemannian manifold, use that as the underlying geometry to generate my network, can I then infer something about the Ricci curvature of the underlying manifold from my network? So basically, is there a discrete version of Ricci curvature for networks? Okay, so just very briefly, in order to understand the punchline is yes. Also, I would not be standing here. I mean, the punchline is yes. In order to explain to you why this definition that I will show you makes sense, I will briefly sort of explain one way to look at Ricci curvature. This is also what I remembered from my course on Riemannian geometry, and this is also the nicest way to sort of understand the definition itself. But there are different ways to look at it. So please indulge me just for this viewpoint. So the idea is you have some point on the manifold, and you have a unit vector pointing in a certain direction. And then what you do is you walk sort of a distance d in that direction. Then there you have a second point. And then what you can look at is you can look at the ball of a certain radius, all points in the ball of a certain radius, and you can look at what happens if I do a parallel transport of all of those balls. So for every ball, I look at sort of the parallel vector, and I transport the balls at this point, the distance delta, according to the geodesic in that direction. So then I get a ball around y. Well, not necessarily a ball, but I get some sort of volume around y. And the question, and then the idea is that if the Ricci curvature of at x in the direction of v, which is denoted by Ricci VV, if that Ricci curvature is 0, it means that basically the volume of this ball is preserved. So the ball in the end has sort of the same volume, right? So if the Ricci curvature is negative, then basically the volume grows. And if it's positive, it shrinks. And so balls on Euclidean space, if you parallel transfer them, they stay the same. On hyperbolic space, they start expanding. On circle space, they start to shrink. Now, this basically gives you some insight into what you might need if you want a more abstract definition of Ricci curvature. Namely, you need a notion of distance, right? We have to talk about points being at a certain distance. We need some way to measure volume of balls, because we want to look at whether or not balls grow or shrink. And for that, we need to be able to compare the volumes of balls. And in general, we want to do this in graphs. We can do it more generally, actually. So what we need is a metric space, of course. Surprise, surprise. In order to measure the volumes of balls, we're going to use probability measures. I'll explain to you how we do that. And then if we have two probability measures, we can compute their difference by using optimal transport distance. And optimal transport distance is already sort of intrinsically linked to properties of these Ricci curvature. So there are many sort of deep connections between Ricci curvature and transport distances. So this is a definition that was not by us, but by Jan Olivier, who in 2009 gave a general definition, a coarse-grained definition of Ricci curvature that works for any metric space. So here X and D is a metric space, and on top of this metric space, we have for every point a probability measure. So for every point, it's a probability measure on the space, on the other points of the space. And then if you take 2 points in the space, then Olivier-Ricci curvature is defined as given here. And so let me explain what this is. So this W1 is just the Wasserstein metric or the optimal transport distance between the two probability measures, the one at X and the one at Y that you have given me, whose formula is given here. And of course, D is the distance. So you look at the optimal transport distance, normalize it by the distance, and it's 1 minus that fraction. Now, let me give you a first argument of why that would make sense, right? Why this would make sense. So let's just consider 2 points on the Euclidean space, right? Yeah. And let me now draw a ball of radius epsilon around point X. And let me consider the uniform measure on this ball, right? So that's the measure mx. And now let me consider a uniform measure on ball Y with a different, potentially different radius epsilon prime, right? So this is my space. Then if both these epsilons are the same, then the Wasserstein distance between these probability measures is exactly the distance. So then this Olivier-Ricci curvature becomes 0. If, however, the probability measure for Y was on a larger radius, the Wasserstein distance actually is larger than their distance, and hence you get negative curvature. And on the other hand, if it was smaller, you get positive curvature. So if balls, in this case, if balls stay the same, you get 0 curvature. If they grow, you get negative. If they shrink, you get positive. This is just to try and sort of explain at a very rudimentary level why this would make sense.
How do you connect the ball size to the target distribution?
Sorry, to which?
How do you connect the ball size to the target distribution around X?
Yeah, so here what I do is basically what I do here is in this setup, I say for every X, I define an epsilon, and then the probability distribution is just a uniform one on epsilon. But we're going to see very specific constructions of probability measures later on when we try to model things and prove things. And also, if you want, there are lots of other sort of intuitions of why this is the right way to do it, and they're all documented in not in this paper, but Olivier has a very nice paper from 2010 where he basically looks at all of the connections between curvature and all sorts of points in physics and other places where he uses intuition to sort of argue why this is indeed the right way to look at it. But he does something more, because he actually proves that it is the right way to look at it if you go back to Riemannian manifolds. So what he did is he considered a smooth manifold, n-dimensional Riemannian manifold, smooth, complete, in order to be sure that you can integrate things, all of these things, you have a volume from these types of things you need. And then what he said is, okay, in this manifold, I'm going to consider the setting where I have 2 points at distance delta, and I'm going to look at uniform random walks for some fixed epsilon. So you fix a delta, you fix an epsilon, and then for every point, the probability measure is the uniform random walk, is the uniform probability on the ball of radius epsilon. In that setting, you can apply his Olivier curvature definition, and then he can prove that if you properly renormalize that basically his curvature is some renormalization of the Ricci curvature of the underlying manifold. That still depends on, of course, the distance between 2 points and the radius. And that makes sense. Curvature is a local property. So if you want something to capture these local properties, you basically need your delta and these epsilons to be sort of small, right? I mean, you need to sort of shrink this space. And in particular, right, if you now renormalize his definition of Olivier curvature by delta squared over 2 times 2 plus the dimension, and you let both delta and epsilon sort of shrink, then it converges to the original Ricci curvature. With respect, of course, to the vector that you use to go from x to y. So this is actually sort of a nice proof to show that this actually makes sense, this definition. So that is nice.
Can I ask something?
Sure, please.
Yeah. So if I remember correctly, I think there was maybe you can correct me. There was an old theorem by I think Hawking and maybe Gibbons or something that showed the equivalence between manifold metric and then a graph, I guess in your language, and the volume form. Right. So I mean, it was already proven that you can take a manifold with a metric and turn it into a graph with a volume, and the volume form, which basically just counts the number of elements in, whatever in which way you decide to discretize. So I'm just a bit puzzled that that's an old theorem, like I don't know, from 70s or 80s. Why is it only in 2009 that people figured out how to take that and build a curvature?
Yeah, no, that's a very good question. So we also, when we started this work, we were also not aware of this thing that one of our collaborators in physics at some point sort of pointed us to this. And these are always interesting questions, right? So sometimes you have that somebody proves something in a certain language, in a certain field, and then at some point later, other people in other fields sort of reinvent the wheel, or at least basically use this result from a different perspective to prove something new. And then you can ask them, okay, why didn't you know about this result?
Right.
Yeah. Sometimes it also has to do with sometimes certain fields. At least in older times, certain people might not talk to each other, right? So this is so this could be a reason, but I don't know. I mean, I guess you would have to ask Jan why he didn't build it directly from this paper. I think in general, what he was aiming for something more general. He was also interested in looking at Markov chains and these types of things, and looking at curvature of Markov chains for finding optimal trajectories in these types of things. So from his perspective, it was way more general than what we are trying to apply it for. So maybe that was the reason, but I can't speak for Jan.
Okay, thanks. Yeah.
Ask you a question.
Yeah.
I think I missed something. When you define a matrix space, each point is a graph distribution, but they are connected. It's like a parameterized family of graph distribution, or it's because it wasn't clear when you define it. So
the general setting is I have a metric space, and for each point I give you some probability distribution. So just for every point, and it can be anything. It can be anything.
But you want it to be smooth, so you must have like some parameters that kind of allow you to transfer from one graph distribution to another one just by shifting some parameter, right? No, in general, I can compute the Wasserstein distance for any two probability distributions, and then in some cases it will make sense, in others not. So the definition is very general, but of course, in order to get some results, we need to choose very specific families of probability distributions and very specific metric spaces. So, but you need it to be smooth. Still, you need to be a Riemann and manifold and things. No, the metric space can be anything. Doesn't matter. Okay. Doesn't matter. No. Any metric space. Now, I think technically it should be Polish. Because else, I mean, I have to define the Wasserstein distance, and if it's not Polish, I run into some problems with integrability types of things. So yes, okay, so there's one technical definition of Polish, but it's very weak. I mean, most interesting spaces are Polish. Yeah, so thanks for that, Jeff. So that's so the nice thing is, so this works. So this is so basically this definition somehow makes sense from the smooth setting. And it works on any metric space, so that means we can apply it to graphs. So let me, so how can you do this? So you take some network, some graph, and then
you use as a metric just the shortest path metric. So that's basically just looking at two nodes and looking at the shortest path between these 2 points, the length of the shortest path. So we need to assume, of course, in this example, the network is not connected, but you need to assume, of course, you need to either assume your network is connected or just look at the largest connected component. But that's the idea. And then you consider what's called the classical random walk measure as your probability measure. So that just means that for every point, the probability distribution is only on its neighbors and it's uniform on the neighbors. So that is what this definition here says. So this corresponds to a random walk where basically at every step you pick one of your neighbors at random and you go there. And then you can, now this is the setup, you got the ingredients, so now you can just define, you get the definition for Olivet curvature in this sense. So you can study this. And in particular, because we're looking only at neighbors, right? So if I want to define curvature, so the distance is always going to be 1. So in this case, it just becomes this. Now this is a classical definition which people studied. So they analyze it on trees and graphs with clustering. It's also, you can relate it to robustness of networks via entropy and heat equations. And then people started applying this notion to analyze robustness and resilience of financial networks, networks of cancer cells, communications, and brain networks, and lots of other things. This is not an exhaustive list. Now you can ask now, okay, that's nice. So this is one way to define it, because I mean we selected the metric space and the probability measure. So this is one way to define this general Olivet curvature. So can you use this definition, this vanilla definition, to uncover the curvature of the aligning manifold? And the answer is no. Yeah.
Can I ask a tiny question? So the second one was the robustness of these networks, right?
Yeah.
So can you expand a bit on what you mean there? Because is that then, if you have positive curvature, it's more stable, and negative curvature, it expands?
It depends on it depends on the several definitions of robustness you might analyze, right? So one is where you just remove nodes at random, right, and then try to see how long does the large connected component stand, and then you, if I remember correctly, then you need basically what you need to do if you want to quickly destroy the giant component, you need to go to nodes that have negative curvature. So if you have a node and most of its edges have negative curvature, so curvature is a definition on the edges. So if a node has most edges of the nodes have negative curvature, if you remove those nodes, then you quickly destroy the giant component. So this has to do with diffusion. So nodes that have diffusion goes faster over nodes that have many edges with negative curvature in this definition.
But I thought negative curvature, but if you move from that node outwards, you don't create cycles, short cycles.
Yes, so
the positive curvature would have some convergence. So intuitively, I would find it more sensible if it's the opposite way around. That if you take hubs, then have more chance of getting cycles happening. And if you destroy the hubs, information that has to flow through.
Yeah, okay, so one of the things I have to say here, so what they studied, so one of the things that they studied here is on graphs that are locally tree-like, right? So then of course you don't have triangles.
Yeah,
indeed, if you have triangles, you need to do a bit more, then it takes much longer if you go from but I think that the results are still sort of comparable, so it's not completely clear how curvature actually helps you to destroy the giant component.
And is this still computationally viable for a large network?
Well, I will show you simulations. We do simulations. So I will come back to, I will come back to this question. The general answer is no. Yeah, no, it's terrible.
I played a bit around with this curvature, and I had small networks, and even then it was.
Yeah, you need to solve these very large. You need to solve these this linear optimization problem, and if you want to push that to very large nodes, the networks, you really need. We had a PhD student who was a wizard in GPU programming and utilizing clock times of processors to optimize his algorithms, and that allowed him to do this for networks of size 1 million.
Really?
Yes, yes. And we were astonished. So we can do it. I will show you some simulation results. We have them.
Is that available?
The code is available, but the problem is it really depends on your infrastructure. So he didn't write a general compiler for any infrastructure. But there's this algorithm available that optimizes specific types of clockworks for specific clock times for specific architecture. So if you would apply it there, then it's optimal. But you can also apply it on other things. But then you need to write your own sort of compiler for the code. But it is available. So just to come back to this question, right, and also have to sort of watch time here. So the answer is no. Why? Well, the problem you can show, and this was already done, you can show that this curvature is bounded always away from -2 and 1. So that means in general, right? I mean, if it can't be any number, right, then this question is definitely no. So then is, okay, but then what should we do? Of course, there are different things we can tweak. So for example, right, these probability measures are quite restricted because they only look at the first order neighborhood. And that was the reason why the distance in this thing basically vanished, because we're only looking at first order neighborhoods. So the idea is, right, we need to extend to larger order neighborhoods, because then basically we get this distance back, and that will help us. So let me try and explain to you what the general setup for Olivet curvature on graphs is. So again, the idea is that we want to sort of imitate this setting for the continuous setting, right? So we want to have this setting where we're looking at uniform distributions on a certain radius for points that are a certain distance apart. So not necessarily distance 1, and so both these things don't necessarily need to be distance 1. So instead of distance 1, we're just going to not only consider direct neighbors, but neighbors that are at a certain distance away. So meaning there's a certain path. And then we're going to use different metrics. So we're not just going to, we're going to consider a general class of metrics, which are weighted shortest paths, meaning that we're going to assign edge weight, and then the distance we're considering is the weighted shortest path. So that means the length of a path is now just a summation of its weights, and the distance is going to be the total weight of the shortest path, the weighted shortest path. And then the question, of course, how do we choose our weights, for example, right? And then we're going to look at different measures on the balls. So we're going to, in general, look at balls that cover a larger set of space, and not only direct neighbors, but second order neighbors, third order neighbors, and these types of things. And then we're just going to do a uniform measure on those. So it's not necessarily a random walk. You can prove under some conditions that if you run a random walk for a certain amount of time, then you sort of cover this, you get to this uniform distribution. But from the theoretical point of view, we're just going to consider uniform distribution on this larger set of neighbors, which is of course very similar to the original setting, right? It should also not be surprising if you look at it like this, that you might be able to prove convergence if you do it like this, because you're just trying to mimic whatever was happening on the continuous setting. So this is when we talked about this with our collaborators from theoretical physics, they say, yeah, okay, this, I mean, yeah, sure, this basically they said, oh yeah, but this is already approved, right? This should work, right? It's just basically translating everything. And then we said, okay, fine. Then we had to sit down. It took a very long time to actually make that rigorous. Turns out really that it depends on the weights that you put on your edges. That makes a difference. So the settings are the following. So I have to first also define how the network is generated, right? So this is once I have a network, then I do it like this. But now I have to tell you how I generate a network. And we do this just very simple. We take a nice manifold, compact, orientable, smooth. Then what we do is we take a number of nodes, which are, of course, we let to infinity in the end. And we take a connection radius, right, that goes to 0. The manifold is compact, has finite volume. So, right, I start sprinkling more and more points. So then I need to sort of decrease the connection radius. Again, this is also because I want to collect a local property curvature. So I need to look at smaller and smaller sections of my manifold. So this is our nice n. What we do is we sprinkle points according to a +1 point process, whose density is just n divided by the volume of the manifold. That means that the expected number of points is going to be n. And then I look at every point and I connect points if they're within manifold distance less than epsilon. That is my model for my random graph. But that's unfortunately not good. That's not what all you need to actually look at curvature, because curvature is about an edge. So to make sure that you can actually prove something, you first need to make sure that there's a specific edge there or a specific pair of nodes there for which you want to compute the curvature. So what we're going to do is we're going to introduce another, that is the measure radius. This is the radius delta that's going to define how far 2 points are from each other. So what we're going to do is we're going to first pick a root in our manifold. That's going to be our point x, together with a unit vector. Then we're going to place another point y at distance delta n in the direction of this unit vector. And these are the 2 points for which we're going to compute the curvature. So we're going to compute the curvature for the point x prime and yn. in this graph. So now what we do, we have these 2 points added. We basically add these 2 points to the Poisson point process. So we still sprinkle the Poisson point process and we still connect everything with the same rules. But basically this makes sure that we know that we have these 2 fixed points, right, that for which we're going to compute the Olivier curvature. Now please note yn is a distance delta n. So as n goes to infinity, yn gets closer and closer to x. This is again, we're measuring a local property. So this is what we want. Okay, so this is the model, but I didn't tell you how to put weights on the edges, right? So this is just an unweighted graph. So the first thing what we do, and this is again, right, we're mathematicians, we're trying to make things as simple as possible to try and prove things. So the first thing we do is basically we cheat. We cheat very much. So let me first sort of say, okay, what we do is we take an n-dimensional manifold, smooth, compact everything. Epsilon is going to be something that scales like the log to some power a n to the minus alpha. So a and alpha are parameters we can tune. Delta, similar with parameters b and beta, again, parameters we can tune. And then we can ask, right, for which conditions of these parameters do we get convergence? But now we're going to cheat. What we're going to do is, for every edge, we're going to put as a weight the manifold distance between the 2 nodes. So basically what we're doing is we're already encoding geometric information in our edges. But again, we need to start somewhere. This is the first thing. It's already not completely trivial to do to prove it in this way. So then we do the shortest way path, as I said, and then indeed we can prove that. I mean, you don't have to read all of this. We can classify all of the conditions for alphas and betas such that indeed, if you properly renormalize the Olivier curvature on the graph, it converges to the Ricci curvature. We can actually prove it converges in a quite strong sense. So this is converges in L1 norm. So it's quite strong convergence. So in particular, what is in lots of things, what this means, these properties in particular sort of enforce that your epsilon is not bigger than delta. So you don't want your connection radius to go beyond the distance where the 2 points are. That's one of the things it does. And the other things that it does is it allows us to tune sort of the density of our graph. It allows us to tune how dense our graph is. So there are several examples. One which is here, where you get a sort of a dense graph. It's not exactly dense because the average degree doesn't grow quadratically, but it grows some sort of as some sort of larger power of n. I think I touched something.
Yeah, it's touch.
Okay, sorry, it's a touchscreen. I will stay away from it. Now you can also go to an almost sparse regime, so you can go all the way up to logarithmically diverging average degree. But we can't go to sparse, but we can go to almost sparse. So even in the almost sparse case, you can still recover this curvature, but you just need to grow your delta needs just to decrease slower and these types of things. But again, as I said, we're cheating because we're including manifold distances. So this is really, okay. This is really to be expected that if you, I mean, it's also sort of a test case because if you can't do this, there's no hope, you can go home, right? So at least now we were happy. And then we said, okay, can we do without these weights? So here, the idea is the following. So if you look at the shortest path distance on this manifold, right, for the graph on this manifold, the intuition is, well, that it's basically sort of a typical edge should be sort of length epsilon n. So if I look at the shortest path length, and if I multiply it by epsilon n, that should somehow be a reasonable approximation of the actual distance between the nodes. That's of course not true in general, right? But I mean, this is sort of the intuition. So basically that means that, yeah, we can just also put the weight epsilon n on every edge. That's the intuition. But actually, it was very nice. We found this paper where they proved that in two-dimensional Euclidean space, so now you do the same construction of your random graph, but then just in two-dimensional Euclidean space, they actually proved rigorously that this is correct. So they proved that if your epsilon sort of grows, if it doesn't shrink too fast, right? So here's the exact sort of formula, like square root log n times n to the minus a half. Then this basically epsilon n times the shortest path distance on your graph is basically converges to the distance in the Euclidean space between these 2 points. Now, why is this important? That's because, again, right? In the end, what we want to do is want to compute a local property. So we're going to take n to infinity basically means that all of these radii shrink. So we're really looking at a small fraction of our manifold. But then, of course, this false fraction of this manifold locally, right, by the exponential map, that's locally sort of Euclidean space with a certain dimension. And then if we now just restrict ourselves to Riemannian manifolds of dimension 2, right, we just let n go be large enough such that we can sort of properly approximate the local neighborhood by two-dimensional Euclidean space, then we can apply this result as a tool to prove our own result. So this is actually what we did. So now we're in the setting of two-dimensional Riemannian manifolds. Again, we have epsilon that is tuned by these two parameters, delta tuned by these two parameters. And now we're going to put define the distance on our graph as just a smallest path distance times epsilon. And then we can prove that in this case, so this does not include any geometric information on the distances, but we can still prove that in this strong sense, for certain regimes of the parameters, we can prove that this Olivier curvature converges to the Ricci curvature of this two-dimensional space. And of course, if you want to go to higher dimensional space, you basically have to, the only thing you have to do is to generalize the results from these other authors, which we contact them, they say, well, yeah, it should be doable, but the math is just going to be, yeah, lots of longer, more, hey, you have to keep track of more dimensions, so nobody really wants to do it, but it should be doable. Now, please note, right, we're not including any information about the true manifold distance. We're just including model parameters, nothing about the true manifold distance that we're including here. So this is really a setting where you have some discrete information from your model, where you can somehow recover in some sort of limit sense the Ricci curvature of your underlying manifold, which is quite surprising, at least from the graph perspective. Now again, these parameters, for instance, in this case, these parameters are such that they have to enforce that your epsilon is still less than delta, but now it has to be really smaller than delta, right? So please note, both of them go to 0, but epsilon really has to go to 0 faster than delta to the power 3. This is just to make, because else the convergence, the results just don't hold up, at least not from our tools.
Does it mean that somehow the graphs that you're getting has some information about the topology of the manifold? Like because in the graph you only have topology, because you're using this distance, right? You don't know anymore. So, but somehow the distance should be somehow still encoded in the topology or in the implicit dimension of the graph or something. Yeah,
it's encoded basically in these regions. So we really pick indeed our delta and epsilon in such a way that we somehow sort of encode the right amount of information about the geometry. And there's this really there's this intricate play between epsilon and delta that allows you to do it. And if you go beyond it, and this is also the trick, right? It's really the trick of having two different radius, one radius for the distance between 2 points and another for the connection radius. It's really the interplay between them that allows you to recover topological information from the graph. Now, one case, we still can't go to the sparse case, but we can go to sort of a non-dense case where the average degree scales as 2 to the epsilon for any epsilon between 0 and 1/6. So we can make this arbitrarily small. So we can't go to logarithmic diverging average degree, but we can go sort of arbitrarily close to constant in that sense, still polynomial. So these are theoretical results. So I can prove to you it converges if n is large enough. But now you can ask, well, how large is n, right? And how does this actually hold up in practice? And then we have to do simulations, and for that we were really happy with this very smart PhD student. So we started doing simulations in the dense case.
Sorry, can I ask a question?
Yeah.
Yeah. So yeah, it's just from my understanding, because I couldn't really understand exactly. But so in physics, you know, people have been trying to do similar things. Like if they want to construct the graph out of the manifold, they sprinkle the manifold with a Poisson process, etc., etc. And the issue there has always been, okay, you can do this way, but now I want to just start with randomly generating a graph, and I want to construct the manifold out of it. Is this something that you have an answer to, or you're still being basing yourself in the existence of the manifold to begin with? Or yes. Can you tell me, if I give you a random graph, can you tell me whether that represents a smooth manifold or not? Are you able to answer that?
Yeah, no. So the short answer is indeed no, but this is where we want to go, right? So what you're asking for is, okay, can I construct a manifold? If I start with a graph, can I construct a manifold such that basically as n goes to infinity, it somehow turns out that my graph is basically the realization of this random geometric graph on this manifold. If I understand
that's the goal in this, also
exactly.
in the physics community, that has been, yeah.
Yeah,
but it's not possible yet. It's not possible.
Well, I don't know how to do it at this point, but I mean, these are first steps in sort of trying to sort of understand whether or not it is possible at all, and maybe getting some idea of how to do it, right? So here, what we really see is that you really have to sort of scan both. You have to scan sort of the local neighborhoods of points that are sufficiently far apart, and then there's this integrate interplay that you need in order to be able to scan sort of at least recover some topological information. So it gives you some ideas of what you might want to do, but I don't have sort of an algorithmic answer to do it or any theoretical results of that.
Okay, thanks.
So basically that brings us to simulation, right? So the question is, how fast does it converge? Our theoretical results only give you some very sort of logarithmic convergence. So that's really not optimal. In reality, it turns out they converge quite fast. So what we did is we restrict ourselves to two-dimensional compact Riemannian manifolds with different curvatures. So we have the torus, curvature 0, we have the sphere, curvature 1, and we have the Boltzmann surface, which is a compact manifold of curvature -1. It's a very nice surface actually, but turns out there are some challenges if you want to compute distances there, which you also had to solve, but it's very nice. And then you can compute. So here are some simulations. So these are the rescaled versions, right? So this is basically, it's this thing, as n goes to infinity. So n is plotted here. So here we go to, we almost go to 1 million nodes, right? So we can push it a bit further, but then it took a bit longer, so we didn't have sort of the same amount of samples to take averages from. And you can see actually it already converges quite fast, right? So about somewhere between sort of say 10,000 and 100,000 nodes, you sort of already get sort of very good convergence for all of these different things. And you can see some interesting things, right? Such that the Boltzmann surface really takes a longer time to converge than, for instance, the sphere. But the sphere is already better than the torus, which was somehow surprising to us. And then we said, okay, this is for the dense case. But now let's go beyond what we can prove and look at the sparse case. So we took this setting, it's just to make sure, and this basically gives us graphs that are sparse, so averagely converges to a constant. And then these are the results from the simulations for different values of alpha that basically give you. And again, you can see they seem to converge. There's a pattern of convergence there. I mean, we can't push it still too far, but there's a pattern of convergence there. And now this is really important because these are settings that are outside the regimes of our theorem. So we can't prove at this point that this also works for sparse graphs, but at least these simulations seems to suggest that even in the case for sparse graphs, meaning that you really don't have that much information, you can still somehow, it's still possible to recover it. So this is something for future work that we're really trying to struggle, because you really need different techniques in order to do this. So that brings me at the end. So I went a bit over time. I hope it was still interesting enough. Everybody's still here, so nobody left. That's always good. So this is just very brief summary, right? So what I did is I basically tried to, in two parts, try to sort of show you this nice relationship, or this powerful relationship between geometry and networks. Where in the first part I showed you how to use hyperbolic geometry to generate models that have these three important properties: sparseness, power law degrees, and clustering. And in the last part, I showed you that there are ways such that you can recover some information about your geometry if your network was generated on some Riemannian manifold under certain properties. And we can prove these things for dense cases, but it turns out indeed that it might also be, there's lots of evidence to show that it should also be true for sparse cases, but we have no clue. We have no clue on how to start to prove that, because our tools really break down at the dense case. We really need logarithmic diverging average in order to make our tools work. So with that, I want to thank all the different collaborators I had the pleasure of working with on both of these two topics. Here are the references to the corresponding papers if you're interested. And I would like to thank all of you for your attention, and I'm happy to answer any other questions that you have.
Yeah, let's thank him for the talk.